iPad is.
So if you can go, yeah. So what did you wind up doing?
I put this microphone. I mean, this
Yeah, but
so this fine. This was the mix. It was all muted. Just turned it on.
okay, the mute's here.
Yeah, both need to be unmuted.
Okay, well, you'll have to show me next time because I've run out of time for.
This thing doesn't work today.
No, he said he couldn't get. He just said he couldn't get it working. Okay.
So we're unfortunately going to have to use the board something that we did the iPad.
What?
Are you ready?
You told me to start recording.
It's fine.
Start, right? It's
Yeah.
streaming, and you told me to hit start recording, which is what I did.
Recording on good meeting.
Which I have not. Which I was about to do when you told me I'm going to start recording there. Okay, I think we're okay.
So is it easier for you when I go to use the board? Should I bring it up in front of the screen and light the screen?
Yes, that will probably be better. That way I don't have to move the camera.
Won't come and go.
That's fine.
So you might remember, maybe, from one of the first lectures, that I said when we were detecting signal, that we would normally define M plus as to be our signal, as MX of T plus now MY of T. And that we then would be using as the detection operator. The detection operator was going to be proportional to F plus, which I said would be the sum of I plus for all the different spins we were detecting. So this must mean that our detected signal, I'm going to stop writing the overbar because we always need the Boltzmann ensemble average. So I should always be writing the overbar. So it's the ensemble average, or the Boltzmann average of the expectation value. But since we always need that in NMR, I'm going to get bored with writing the overbar. So I'll stop writing the overbar. And just understand that we always need the Boltzmann average. Our definition would be that this was then, for example, if we just had a single spin, we would mean by this the trace of F plus with the density operator. And then recall that, well, let me write this as I cross. And then I could write, of course, the density operator as some expansion. Now I'll have the sum of I plus some basis operator. coefficients from the expansion of the density operator. And I can write this. What's the Hermitian conjugate of I plus? So if I take the transpose and the complex conjugate, I'm going to get I minus. And now if the operator basis is orthogonal, this is 0 except for I minus. Right? When B sub k is I minus, I get 1. And if B sub k is any other operator, I'm going to get 0. So this just picks out then the coefficient B sub k that corresponds to I minus, which I normally would just write as so this is to illustrate something peculiar about this quantum mechanical formulation. Our signal is n plus. The operator component that we care about is I minus. So there's a switchover because of this formula here. Our detection operator is I plus, but that ends up picking out the I minus part of the density operator. So what we detect at the end in the experiment is going to be the I minus part of the density operator. All the other parts of the density operator we can throw away at the time we start acquisition. So that's, of course, a great simplification, but also usually kind of confusing. You take the I minus part of the density operator to get the n plus detected signal. And of course, if we have the transverse operators, Ix is going to be 1/2 I plus I minus, and Iy is 1/2I plus minus I minus. So if we have transverse X magnetization, we pick out this part of it. And if we have transverse Y magnetization, we pick out this part and multiply by 1/2 and multiply by 1/2I. So quite commonly, we won't think of during acquisition about I minus, but we'll think about the signals that come from Ix and Iy, recognizing that they contain I minus. Later on, when we talk about phase cycling, we'll say, when I'm doing phase cycling, that we detected a coherence level of -1. And that's because of this. We'll think of I minus as being coherence order -1 when we talk about coherence orders. So detection of -1 coherence is really coming back to this calculation. So here, then, let's go through let's go through some calculations to illustrate this. So we start with Z magnetization, apply a Y pulse, have magnetization on the plus x-axis. And now the magnetization starts to process around the plus x-axis, or around the z-axis. So IX processes around the z-axis, and we have a Hamiltonian that consists of chemical shift and scalar coupling. And again, I've played my game. I should have done this in we'll come back to it. So I played my game of writing IX in terms of I plus and I minus, and also inserting the identity operator here for the S spin, where the identity operator was S alpha plus S beta, and that gave me 4 terms. And then I calculated the evolution for each of the 4 terms. And we will not normally do it this way, but maybe do it this way for what comes next. But in any event, we have these various terms. And now we have the detection operator I minus. And again, if I would like, I can insert the identity operator again is S alpha plus S beta. So here's my density operator during acquisition. And I said I just need to pick out of this the part that depends on I minus. But since I can always insert the identity operator here as S alpha plus S beta, that's the same as picking out from here the I minus S alpha part and the I minus S beta part. So that's what's happened here. I've just taken those parts and then calculated the trace. So I have, as we expect, an in-phase doublet. One doublet component shifted by plus pi j, another doublet component shifted by minus pi j, centered on the frequency omega I. And there's some constant proportionalities that are missing. Suppose by hook or by crook, we generated this density operator. I can expand it in terms of the raising and lowering operators and S alpha and S beta in the same way. Ask how it evolves. Here's the density operator again. It looks just like the one I had before, except there's some minus signs corresponding to that minus sign. And again, I pick out the parts that depend on I minus S alpha and I minus S beta. And take the trace and end up with this. And now, as we talked about before, we have an antiphase doublet. One member of the doublet component is positive, the other member of the doublet component is negative. What would happen if J was equal to 0? If J was equal to 0, these terms identically cancel each other. So this operator here generates an antiphase doublet if the J coupling between the I and the S spin is not 0. the J coupling was 0, there's no signal, as we see from this result. Because essentially the two components would be sitting on top of each other, one up and one down. So here I've done this in a slightly different way. So the signal is the trace of the density operator as a function of time with F plus. But it turns out the trace is invariant to cyclic permutations. So I've taken this part. This should have been over here. I propagate sigma 0 forward with this kind of e to the minus IHT, sigma 0, e to the plus IHT. But because the trace is invariant, I can move this part over to here. And now it looks like instead of the density operator evolving forward in time, it looks like the detection operator is evolving backwards in time while the density operator is staying stationary. And now I take the detection operator, again, write it as I plus SL S beta, evolve it backwards in time, carry through the arithmetic, do the trace, and I discover that my signal then is the trace of the operator representing one doublet component with the initial density operator. So it picks out of the initial density operator the amount of this doublet component and assigns it this frequency. This picks out of the density operator the amplitude of the other doublet component and assigns that this frequency. So since I already recognize that this will evolve at the frequency of the I spin shifted by the scalar coupling, and there's not really any need for me to ever calculate this. I know that answer. I just need to say, does my density operator contain any of this operator? Actually, because of the bar, does it contain any I plus? I minus. Or, over here, I just ask if the density operator contain any I minus S beta. I don't actually have to do the calculation of evolution. So you think, when you do the NMR experiment, that or when we analyze a pulse sequence, that you analyze the detected signal, but we don't actually ever have to analyze the detected signal. We know what the detected signal will look like as soon as we identify sigma 0, the density operator at time 0 of the acquisition. What happens after that, I mean, is important in practical terms. We actually do have to record a signal on the spectrometer, but for understanding the pulse sequence, we don't need, or to understand the experiment, we don't need to bother with evolving the density operator during acquisition. We just pick out the parts of the initial density operator that we know will be detected, and we know the detected parts are always going to be the multiplet components. So if we know the J couplings and the chemical shifts, we know where all the peaks are. Our only question is, what's the amplitude of the peak? Is it 0? Is it positive? Is it negative? Do we get what kind of double multiplet structure are we getting? So this is a great simplification because calculating the evolution of the density operator through the acquisition period generates all sorts of terms. But there's also this trick of the cyclic permutation of the trace is frequently useful in other contexts because we can shift around it, as I did here, instead of the time dependence of the density operator and the time independent detection operator, I now have a time independent density operator and a time dependent detection operator. And depending on context, the ability to shift what I regard as time dependent from one operator to another is sometimes quite useful, as it is here. So this leads to rules that seem to have disappeared. So let's suppose we start with IZ magnetization, apply a Y pulse, and we get IX magnetization. And we know that then this is equal to IX S alpha plus S beta if I put in the identity operator. And because the signs here are the same, this is going to be a doublet component where both doublet components have the same sign. So this means I'm going to get an in-phase doublet. So if I have a transverse operator IX, and the coupling partner is the identity operator, I know right away I'll get an in-phase doublet if there's a J coupling. If there's no J coupling, these two will be on top of each other and I just get a single. So my first rule is IX E, or say the S spin, which is just IX. The way I usually write it, this will be in phase doublet. So I don't need to do the calculation. If at the start of acquisition, I see IX, I say right away my signal will be an in-phase doublet. No calculation needed. What about this chemical shift evolution? So IX is 1/2 I plus I minus. And I'm going to pick out the I minus part. And I will call this the absorptive signal. You'll see why in a minute. Absorptive Lorentzian. So if at the start of acquisition I have an IX operator, I say I'm going to have an in-phase doublet and it's going to be absorptive. The line shape will be absorptive, which is this shape. The shape you're used to. Except it'll be split into a doublet. What about IY? IY is IY S alpha plus S beta. So this is also an in-phase doublet. IY, which is the same as IY E sub S, is an in-phase doublet. And then what about chemical shift? This is 1 over 2I, I plus minus I minus. And I just want the I minus part, which is 1 over 2I, I minus 1 over 2I, I minus, which is the same as I 1/2 I minus. And what does the I mean? I don't detect imaginary signals on the NMR spectrometer. But recall Euler's relation that says E to the theta is cosine theta plus I sine theta, e to the I theta, sorry. So I can think of e to the I pi over 2 is equal to I, right? Because cosine pi over 2 is 0, sine pi over 2 is 1. So this is a definition of I, and that means I can write this as 1/2 I minus e to the I pi over 2. So that this is a phase factor on the signal, where the signal is going to be going as E minus I, say, omega t, e to the I pi over 2 now, which is the same as e to the I minus omega t plus pi over 2. So this is a phase, right? I have a frequency times a time plus a phase. So this says that IY generates a signal that's phase shifted by 90 degrees relative to the signal that comes from IX. And if I call IX the absorptive signal, 90 degrees out of phase is the dispersive line shape. So this will give a line shape that has the dispersive shape. So I don't have to do the calculation. Every time I see IY at the start of acquisition, I say I have an in-phase doublet and the line shape is dispersive. Every time I see IX, I say I have an in-phase doublet and the line shape is absorptive. Of course, you usually don't like dispersive line shapes. So when you see a dispersive line shape, you think, well, I'll just phase correct it. If I phase correct by 90 degrees, this becomes absorptive. But you have to remember, if you had both IX and IY present, if you phase correct the IYs to become absorptive, the IXs then become dispersive. So what's important in NMR is always the relative phase of things. And we just have to sometimes be careful that if we apply a phase shift, that it gets applied to everything. So we can't somehow miraculously, in the spectrum that has both IX and IY, phase correct to get everything to be absorptive. And we'll see examples of that. But if the signal you want turns out to be proportional to IY, you're free to think of that as you mentally apply a 90-degree phase shift to make it absorptive, just remembering that all your IXs become dispersive. So those are our first two rules. We just inspect the density operator at the beginning of acquisition. For every IX, we say we get an in-phase absorptive doublet. For every IY, we say we get an in-phase dispersive doublet. What about two IX SZ? This is 2IX times 1/2 S alpha minus S beta, where I've substituted in for SZ its definition. This says then that I'll get an antiphase doublet, and the IX term says once again I'll have an absorptive signal. So 2IX SZ gives me antiphase doublet, and it's absorptive. If J is unequal to 0. If J is equal to 0, this never evolves with respect to the J coupling, and will give a 0 trace with I minus. Because if I take this, the part of this that depends on I minus, because there's a factor of a half. If I pull out the part of this that depends on I minus, the trace of this is 0, which you can prove to yourself by going back and looking at the matrices, multiplying them together and taking the trace. But you can also think of it as that we've done a partial trace over the I minus part, over the I spin operators, and we only have one S spin operator, and the trace of SZ is 0, which drives the whole thing to 0, because SZ is 1/2, 1, 0, 0 minus 1, so its trace is 0. We need to get rid of this SZ operator by evolving under the J coupling, so that we come back to an operator that's non-zero with respect to I minus. So people will talk about detecting the antiphase operator, and that's a bit of shorthand. What we detect is the I minus operator that evolves from the antiphase operator during the acquisition period if the J coupling is non-zero. But that's a big mouthful to say, so nobody says that. But we have to remember, if J is 0, this will always be a 0 trace then with the detection operator and won't generate any signal. Is that part clear? And then 2IYSZ is then antiphase and dispersing. Again, if J is unequal to 0. So we have 4 rules that we can just apply to the state of the density operator at the beginning of the acquisition period, and then decide what the spectrum will look like. What about, suppose we generated something like this. At the start of detection, what happens? Well, this we could write as 2I plus I minus over 2 and 1 over 2I S plus minus S minus. We multiply all this out, we get 1 over 2I plus S plus minus I plus S minus plus I minus S plus minus I minus S minus. We call the sum of the number of pluses and minuses the coherence order. So this would be coherence order plus 2, coherence order 0, coherence order 0, coherence order minus 2. The plus and minus 2s are called double quantum coherence. And the coherence order 0s are called zero quantum coherence. We also apply the Z operators, we also call coherence order 0, which kind of mixes things up a bit. That's the way it is. So none of these have a non-zero trace with I minus. We need the J coupling to evolve in order to get back to an I minus operator. For the same reasons that I just talked about. We can imagine taking the trace with I minus or with I plus, and the partial trace of S plus and S minus will drive everything to 0. So the J coupling would have to evolve to make this detectable, just like the J coupling has to evolve here. So you were supposed to think about what you thought about the J coupling for this kind of term. Would anybody reach any conclusion about what they think about the J coupling evolution for an operator like this? Perhaps it's easier to see if we thought about this operator. Remember our shorthand said that we wanted to know, I'll bring the screen up. Right, our shorthand asked what the relationship between three operators was in some commutator sense. So the operator for the scalar coupling is that. So we'd be interested in knowing what that commutator is. And if we work out that commutator, which you might do by taking the matrices and multiplying them together, or having Mathematica do this for you, you get 0. So J coupling for the multiple quantum terms don't evolve under the J coupling. So this can never evolve under the J coupling into something we can detect. So all the multiple quantum terms are just ignored for acquisition purposes. And I said that it was worth thinking about the energy diagram. So I'll go back to the picture. Go back a ways. Oh, maybe it's not even, might not be in this presentation. Well, this will do. So what happens to this energy? Well, we have no J coupling, and now I turn on the J coupling. The energy for the J coupling is 2 pi mi ms times the operator, where mi and ms are the quantum number of each state. So here I have a half and a half. So I multiply those together. I get plus a quarter times 2 pi j. So the energy shifts up by 1/4 times the J coupling, basically. What happens over here? I have a half minus a half. So the J coupling shifts down, shifts the energy level down. What happens to I beta, S beta? Shift up or shift down? Shift up. Minus a half times minus a half is plus a fourth. So the energy level shifts up by 1/4 times 2 pi j. And what happens over here? It shifts down. So the double quantum terms connect these two energy levels. How does the energy change when I turn on the J coupling? What's the energy difference between those two states when I turn on the J coupling? 0. They both shifted up by 1/4 times 2 pi j. The zero quantum terms connect these two energy levels. What happens to that energy difference when I turn on J? Also 0. They both shifted down by 1/4 of 2 pi j. So the J coupling doesn't change the energy of the double quantum transition or the zero quantum transition, and therefore the J coupling can't lead to any evolution of the zero quantum terms or the double quantum terms. So we could have gotten the answer that the J coupling won't affect the zero and double quantum terms by working out this commutator. Or we could have come back to the energy level diagram and reasoned it out quite easily by asking what are the changes in the energy level diagram. Here, this is the single quantum transition of the S spin. The S spin changes from alpha to beta. The I spin, nothing happens to. This energy level went up. This energy level went down. The energy difference was reduced by 1/2 times 2 pi j. One went up by a quarter, one went down by a quarter. The energy difference changed by 1/2 times 2 pi j, which is pi j. So that multiplet shifted by pi j, which is what we've seen in all the other pictures. Here's the other transition, single quantum transition on the S spin. The S spin goes from alpha to beta. The I spin stayed beta. This energy level came down. This energy level went up. So the energy difference there increased by pi j, and that's the doublet component that shifted in the other direction by pi j. So again, the math is reflected here in the energy level diagrams, which is always comforting. So we spend a lot of time thinking about these operators and transforming the operators, but every so often it's a good idea to check back at the energy level diagrams. And here are, in fact, what I just said about the transitions. So this operator that we call I minus S minus changes, I minus changes alpha to beta. So this changes this alpha to a beta. This changes the S alpha to a beta. So we go from I alpha, S alpha to I beta, S beta. I plus S minus does the other thing. It takes beta to alpha and beta to alpha. Here are the single quantum transitions. This took alpha to beta while leaving, or took S alpha to S beta while leaving I alpha unchanged. That's just this picture here. I alpha state. So I can label up all of these transitions with labels. Now, for two spins, we have 4 energy levels, right? So our operators were 4x4 matrices, and we expanded up from the 2x2 matrices using the direct product. So the operators are 4x4 matrices, which means they have 16 elements in the matrix, which means the operator basis has 16 elements in it. We could always write a matrix with a 1 in one of the positions in the matrix and zeros everywhere else. So I should have 16 operators here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 4 operators representing the populations. So I alpha, S alpha would represent the population of the alpha alpha state, I beta, S beta would be the population of the beta beta state, so on and so forth. So I represent the 16 operators here. 4 operators for populations, and then 2 double quantum transition operators, 2, where the 0 from? 2 zero quantum transition operators, 4 operators representing the I-spin single quantum transitions, and 4 operators representing the S-spin single quantum transitions. So again, what's nice is our math, these symbols, reflect back the things on the energy level diagram. Now the tricky part is we understand what the populations are. Because we can, in principle, go count how many spins are alpha and how many spins are beta. What do I mean by these squiggly lines? Well, these squiggly lines in NMR are called coherences. And I skipped over this, yes. So let's take this element of the density operator. So this is the alpha-alpha component of the density operator. And if I remember that actually left something. Oh, I'm sorry, the spacing got screwed up. There should be a big space here. So this is just the expansion coefficient, magnitude, ensemble average. This is the same thing here. But the cross terms, remember a complex number has an amplitude and a phase factor. So I could always write the some slide that got lost here. Move this over so it's in the camera. And the nth element of the density operator way back when got defined as this way. Now my memory is failing me. This one. The average over the expansion coefficients from expanding the wave functions in terms of the basis. But these are complex numbers, so I could always have written a complex number C, for example, could be its magnitude times its phase. Is a way of representing, one way of representing a complex number. So if I have sigma alpha alpha, right, then this is C alpha squared, and then e to the I phi alpha. But then I have the complex conjugate, e to the minus phi alpha, and those are unity. And I just end up with C alpha squared, the magnitude squared, which I then interpret as the population. But if I have this term, what I mean by this is C alpha magnitude, C beta magnitude, e to the I phi beta, e to the minus I phi alpha. I need the averaging here. These don't vanish. And now let me for a moment assume that I can average separately the magnitudes and the phases. It's a complicated detail, and let's pretend that. Just to show you what I want to show you. So this is some angle, and then I'm averaging it over the ensemble, the Boltzmann-weighted ensemble, meaning for different sub-ensembles of the spins. What do you suppose if I take a sample of water off the laboratory bench, put it into an NMR tube, put it into the NMR spectrometer, and then ask what the phase is for some ensemble of spins in one part of the sample compared to another part of the sample. Any reason for thinking those phases are correlated with each other? And we barely have any idea what we mean by phase here, so it's hard to imagine there's any correlation. The random phase approximation says that if we have a sample at thermal equilibrium, Boltzmann equilibrium, these different sub-ensembles in the sample aren't going to have any phase correlation. This e to the I times an angle are just sines and cosines, right? If I again use Euler's relationship, I'm just averaging over sines and cosines of random angles. So what's the mean going to be of that? It's going to be 0. I'm going to have all the possible angles between 0 and 2 pi appearing billions of times, and the average is going to be 0. So, and that means these off-diagonal terms will vanish. We'll just have the on-diagonal terms proportional to the population. So that's our Boltzmann equilibrium, another statement of the Boltzmann equilibrium density operator is we only have diagonal terms because there's no phase correlations between the different spins in the sample at Boltzmann equilibrium. But now, if I generate IX magnetization, which hopefully IX magnetization, right, was this is IX. So if I have IX magnetization, the off-diagonal elements can't vanish. So this can't be 0 anymore. And when that happens, we say we've generated some coherence. That there is now some phase relationship for sub-ensembles in different parts of the sample, averaged over the whole sample. Well, how did that come about? It came about by the pulse. So I started with 90-degree magnetization, and I rotated, say if I applied a Y pulse, and put the magnetization onto the x-axis. Why didn't this happen? Suppose this had happened. I have really all of these little spin packets in the sample. Suppose one rotated here, one rotated there, one rotated there, one rotated there. So that when I look down from the top, they were all pointing in different directions in the XY plane. And then they would all add up to 0 again. Because it would be just as likely to have one pointing along plus X as along minus X. So why didn't this happen? Why did everything rotate to the x-axis? What does that mean about the RF pulse over the volume of the sample? What had to be true about the phase of the pulse in different parts of the sample? What would have happened, make the case simple? Suppose in half the sample the pulse was X phase, and the other half of the sample the pulse was what? Minus X phase. Then half the magnetization would rotate to the minus y-axis, and the other half would go to the plus y-axis, and those would exactly cancel each other. So what has to be true about the phase of the pulse in different parts of the sample? It has to be the same. And that means we have to generate over the macroscopic volume of the sample RF packet that spatially has the same phase. If that wasn't the case, if we generated a random phase at different parts of the sample, we would just spread the magnetization into the XY plane. There'd be no net XY magnetization. There'd be no Z magnetization left if it was a 90-degree pulse. And we would say we've saturated the system. And if you do UV vis, this can happen. Your typical UV vis lamp is not spatially phase coherent. Right? You're generating photons by heating atoms in different parts of a wire, and there's no reason for the photon that's emitted from one atom to be correlated with the photon that comes out of the next atom. So the photons have random phases, and that means, in the analogy, you're going to be able to saturate the system, but you can't generate anything like a transverse coherence in using your normal UV vis machine. If you want to do that, you have to go buy a phase coherent laser that generates laser pulses that are phase coherent over some appreciable volume and some appreciable time. And that usually means you have to buy a very expensive laser. It turns out that because the wavelengths are so long for radio frequencies, that it's very easy to generate phase coherent signals. And all of radar and radio electronics depends on being able to do that. And it's really a factor of the wavelengths being so long. So we're able to do it. We're able to generate a phase coherent pulse over a macroscopic volume, and that means we can rotate all of the subpackets so that they mostly end up pointing in the same direction. And there's a little bit of phase dispersion, not very much on the modern spectrometer. The phase purity of the RF pulses is really quite remarkable. And that causes this average not to be zero. And then we see the transverse magnetization reflects then this phase coherence between the little magnetization packet generated for each of these imaginary subensembles in our larger sample. And as I said, that's what we call coherence. And that's what we represent by these squiggly lines. And do you want to add something more sophisticated from the solid state perspective on the meaning of coherence?
Just about the phase of the pulse, that because you're in a resonant device with a high Q, there probably isn't any way to have it anything except all the same phase.
But we have a different problem, which is jitter in the phase over time. So the oscillators that create the RF are really pretty clean. But, you know, if you got something from a lesser manufacturer or whatever, the problem is more a jitter in the phase over time. But in space, we don't have a way of generating that. But now, a third thing is the so-called phase transient. So when you put a square pulse, does it come on X right away, or does it go off of X right away? And that's where there's still room for improvement. So you talk about purity of phase, like lots of different aspects, right? And it's this last one that is an actual issue for some experiments. That you can see the amplitude settles down in a certain amount of time, but it can take the phase even longer to get there.
And you might notice on the Brooker spectrometer, there's frequently lots of little 2 or 3 microsecond delays in the pulse sequence to give time for the phase to settle before a pulse. Which can be a big annoyance.
Yeah.
It actually also means there are times in an NMR experiment where you might actually want to saturate the signal. And it's actually harder to do than you might think, because we have these very phase coherent pulses. And James Keeler once did an experiment where he crushed one of the coils in his probe in order to make it perform extremely poorly, and use that one for saturating, and then the other coil for actually doing pulses. He wrote one paper about that. I think never used that probe again for rather obvious reasons. I don't recommend it to you unless you own the probe. So of course we could have more than one J coupling. And here are diagrams for 3 spins with the different states, alpha, alpha, alpha. I haven't put all the squiggly lines on, but we could draw the same kinds of squiggly lines, and that would connect here, for example. This would be a single quantum transition. If we call these IRS, this would be a single quantum transition of the I spin, where the R and S spin stayed in the alpha state. And then I would have, here is a single quantum transition of the R spin, where the I and S spins stay in the alpha state, so on and so forth. So I could label these all up with these same kind of labels, where I would, for example, call this one I minus, if I had a squiggly line going this way, this would be I minus R alpha S alpha, and so on and so forth. And then I can work out what the multiplet pattern is going to look like for each of these. And so that ends up meaning, if I have operators in a 3-spin system, what will I get for something? What spectrum do I expect to see? Now I have 3 spins. I, R, S. What do I expect if I notice at the beginning of detection that I have IX operating? Well, I can always imagine that as being composed of, right, the identity operator for E and the identity operator for R. If there is a JIR coupling and a JIS coupling, then I expect to see a doublet of doublets. I'll have an absorptive line. There'll be one doublet splitting to the R spin and another doublet to the S spin. If there was only a JIR coupling, then I'm going to have a doublet with respect to the IR coupling, and then a singlet because there's no coupling to the S spin. Let's suppose that JIR was bigger than JIS. So the first splitting, I think this would be JIR. And then each of those gets split by the JIS coupling. So I end up with a doublet of doublets. And when you're working these out, it's easiest to start with the largest coupling and work your way down. The easiest way to get the multiplet pattern worked out, because then the lines don't cross each other, which is confusing. So if this was the R spin in the alpha state, this then is, assuming the couplings have the same sign, those are the 4 states of the coupling partners. The R spin is alpha or beta. The S spin is alpha or beta. Of course, if the signs of the couplings change, these swap around their identities because the couplings could be negative. Well, that's just kind of a detail. What about, so our rule is, if we have a transverse operator, we're going to get a series of in-phase doublets. And again, absorptive phase. If this was IY, we would get dispersive phase in a series of in-phase doublets. What about if we had 2 IX RZ? This would be the same as putting in ES, so that I know here I'm going to get an antiphase doublet with respect to the IR coupling, an in-phase doublet with respect to the IS coupling. So how does that change my picture? Again, if JIR is largest, I now have an antiphase doublet with respect to the IR coupling, and each of these gets split into an in-phase doublet. So I end up with an in-phase doublet there, and this one becomes antiphase, splitting over there by the JIS coupling. So each Z operator gives me an antiphase doublet. Each identity gives me the in-phase doublet, as long as the couplings are non-zero. If I had an operator like this, and there is no IR coupling, then I'll get no signal at all. Because this has to be able to evolve back to I minus, and we need a non-zero J coupling for that to happen. If we had two transverse operators, of course, then we're back to having double quantum coherence, and there's no signal at all. We should really do this then on the board. Well, we have all the rules we need for quite a while. We can now analyze, if we continue to forget about relaxation, we can now analyze virtually any at least solution NMR pulse sequence. Let's go back and then do let's do this then for the IS spin system. And we'll assume both I and S are hydrogens. And now we just have to apply our rules over and over again. Now, in this sequence, since I and S are going to be hydrogens, they're both going to be affected in the same way. So I'm just going to work out the results for the I spin, because then we can just swap all the labels to figure out what happened to the S spin, because it's going to be completely symmetric in this case. So if we start with IZ, and now we apply a 90-degree Y pulse, what's the operator that we end up with? IX, thumb along Y, fingers on Z, we rotate to the plus X-axis. Let's put a little diagram over here. So we get plus IX. Now, during this period, we'll get evolution under the chemical shift and evolution under the J coupling. And we can do them in either order that we want. So let's do the chemical shift first. The magnetization precesses around the Z-axis towards the plus IY axis. So under the chemical shift, I get IX cosine omega t plus IY sine omega t. Now I have to do the J coupling. So let me make a little picture, say for this. So I have IX. The Hamiltonian is now 2IZSZ. And that means over here I want 2IYSZ, because I'm trying to work out what's happening to IX magnetization. So I put the coupling Hamiltonian here. This is the operator I'm starting with. And then I label the other operator if I need to. And again, the rotation says that I'll have Ix will become Ix cosine I j tau, which would be tau, plus 2I z Iy, SZ sine I j tau, all multiplied with cosine omega tau, which was just a numerical factor that came along for the ride. And now to do the same thing to Iy, I'm going to make a little picture, 2Iz SZ. I'm starting with Iy, so I have to put the two-spin operator over here. And now what happens? Iy is going to rotate towards minus 2IXSZ. I'm just going to rotate back into the board to the negative axis so that this becomes Iy cosine I j tau minus 2IX sine I j tau sine omega tau. And you can see when I multiply everything out, I get 4 terms. And you'll see those same 4 terms come up over and over again, because it's almost always the case that we follow a 90-degree pulse with some delay. So we're always going to get these same 4 terms in the beginning. And now we have, if we want to spin echo, a 180-degree pulse. And it's non-selective, so it's going to act on both the I spin and the S spin. I have to work out the effect of the pulse on all the operators. If the I spin was nitrogen and the I spin was hydrogen, I could pick which channel I turn the pulse on. Do I want to apply the pulse to hydrogens or to nitrogens? Here, I'm presuming everything is hydrogen and I'm applying a non-selective pulse. So both I and S will see the effect of the 180. So what will an X rotation do to this X operator? Nothing at all. So I just end up here with Ix cosine omega tau cosine I j tau. I brought the cosine in. What does the 180 repulse do to Iy? Minus Iy. Okay. My thumb along X, my finger along Iy, 180 degree brings us to minus Iy. So this will become minus Iy. What does 180 degree X pulse do to SZ? Minus SZ. So I have minus Iy times minus SZ. The minus signs cancel. So here I just get plus 2Iy SZ sine I j tau cosine omega tau. Iy goes to minus Iy. Minus Iy cosine I j tau sine omega tau. Here, nothing happens to Ix. Sz goes to minus Sz. So I have plus 2Ix Sz sine I j tau sine omega tau. Everybody happy with that? And now I have to evolve each of these again for another time period tab under the chemical shift and scalar coupling. And so this is going to turn into 4 more terms. This is going to turn into 4 more terms. This will turn into 4 terms. This will turn into 4 terms. So I'm going to end up with 16 terms. And then I'm going to want to try to simplify them all with trig identities. And hopefully, so here's where we are after the pulse that rotated both I and S. I indicated that here by writing both IX and SX. And then here's the shift evolution in the second time period. So that took 4 terms and split it into 8 terms. And then to make my life a little easier, at this point I tried to do some trig simplification. And if you notice here, I have IY cosine squared omega I t cosine pi jt. And down here I have IY sine squared cosine. And sine squared plus cosine squared is 1. So I can combine these 2 terms to get 1. And here, these 2 terms cancel each other. These are the same terms with minus signs, so they cancel. Here I have sine, cosine, minus cosine sine, so that cancels. So I worked through some trig identities here. Of course, the first time I did this, I wasn't smart enough to do the trig identities. I did all 16 terms and then tried to sort them out. But in this particular case, we can take these 8 terms and work them down to this, and now do the J coupling. So I end up with 4 terms from working out the J coupling, and then there are also some trig identities to be applied, and I end up with this result at the end of the day. So I apply the rules. I have to learn my trig identities, or learn to use Mathematica to simplify the trig identities, and then I end up here. So what happened? The chemical shift went away. Right? We worked this out in the block equations, that the spin echo refocuses the chemical shift. But the J coupling looks like it went on for a time period 2t. The J coupling was unaffected by the 180-degree pulse. It evolved as if the 180-degree pulse wasn't there. And this turns out to be, of course, generally true. The spin echo will refocus chemical shift evolution, but homonuclear J couplings evolve through the spin echo. That means from now on, when we see a spin echo, we know the answer. We don't have to work this out in detail anymore. So one of the tricks in analyzing complicated pulse sequences is that we build up a mental image of blocks where we know what the blocks do. So we don't have to do a detailed analysis of each block. Now we also could have, in this case, done the whole sequence all the way through the sequence with the J coupling, and then go back, having seen that the J coupling was refocused, then go back and do the scalar coupling. One has to be a little careful when there's more 90-degree pulses, because 90-degree pulses sometimes mix everything together. But when you have trains of 180s, it frequently is easier to just do all the J couplings, or do all the chemical shifts and then all the J couplings. But if you can go back and for yourself work this out and get the same answer with the chemical shifts refocus and the J coupling just evolves for twice for the total time period, then you're in business. You can then analyze pretty much any experiment. What signal do we predict at this point? If we were going to turn on the detector now, looks like there's something wrong with signs here. That's probably just, that should just be a minus sign, one minus sign. What do we predict? Here we say we'll have a dispersive signal, but in phase. Here we get an absorptive signal, but it's antiphase. They'll both be at the I spin frequency. This with the transverse operator is I, so this will evolve the chemical shift of the I spin. The transverse frequency here is I, so we'll get the I spin frequency. So we'll get an in-phase doublet that's absorptive sitting on top of an antiphase doublet that's dispersive. And the relative size of those two signals superposed on each other will depend on the value of this cosine and sine. If I set this, suppose I set t so that this was equal to pi over 2. In that case, this would vanish and I would only see the antiphase doublet. On the other hand, if I set this equal to pi, set t so that this was equal to pi, then I see the absorptive doublet, I see the in-phase doublet, and the antiphase doublet is null. And in between those, I'm going to get some admixture of the two. That's going to be kind of an ugly spectrum in general. But we'll see how we make use of this sort of thing going forward. But I don't have to now evolve through acquisition. If I now turn on the receiver to record the signal, I don't have to do any more calculations. I just look at this and say, this tells me the signal type and what frequency the signal will be and what the chemical shift will be. This tells me just the amplitude of that signal. That's just a scaling factor. Shape of the signal and what frequency it will be at. And this just, again, tells me the amplitude of the signal. So next time I think we start on then using this for multidimensional NMR. We have enough theory now to analyze 2D spectra, and then 3D spectra and 4D spectra are just trivial extensions of 2Ds, even though they might be complicated in practice from the theoretical standpoint, they're quite simple. So see you tomorrow. But try to get this worked out on your own, because you can do this. Basically, everything else is just doing the same crank, turning the same crank over and over and over.